So, is my screen visible to you, students?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yeah. So, in yesterday's lecture, what we have seen, we try to understand what is meant by that hydrodynamic bearing, or what is your sliding contact bearing. And then, along with that, I try to explain you the other type of bearing, that is your hydrostatic bearing. So, as far as the hydrostatic bearing is concerned, so here is your this a pump, which is an external means that we are using for generating the pressure, whether it is a hydrodynamic bearing or a hydrostatic bearing. It is the pressure of your lube oil which is going to take up the external load. Okay. As far as the bearing is concerned, so one of the main function of your bearing is to support the load coming on your shaft. Okay. So to take up that particular load, here what we are doing, we are making use of that pressurized fluid, pressurized oil. So in case of your hydrodynamic bearing, what I told you yesterday, that pressure in the lube oil is developed due to the relative motion between that of your shaft and that of your bush, yeah, bearing. And in case of your hydrostatic bearing, that for generating the pressure, that relative motion of your shaft and the bearing, that is not at all responsible. We are making use of that external means, so that easily you can control the required pressure. Okay, but when you are going to make use of this external means, I mean when you are using that particular pump, so that time no doubt ki operation of your that hydrostatic bearing will become a much smoother in comparison to your hydrodynamic bearing. But the thing is that key the additional cost of this hydrostatic additional cost of that pump will come in your hydrostatic bearing. Okay, now let us start. Also I talked about I talked about what are the advantage. I think I didn't discuss this particular point with you. As far as the advantages and the disadvantages are concerned regarding that hydrodynamic bearing and hydrostatic bearing. So, as I told you here, in case of your hydrostatic bearing, we need this particular pump. Okay, so if you see the overall construction, overall design of this hydrostatic bearing, so due to the use of that particular pump, due to use of the various valves which are going to regulate the flow of that oil, pressurized oil to your that bearing. So due to that, this design of your hydrostatic bearing, you can say it is slightly complex in comparison to your hydrodynamic bearing. Okay. On the other hand, we can say that as far as the design of your this thing is concerned, hydrodynamic bearing is concerned, we can say that the design is design of your design of that design of your hydrodynamic bearing is relatively simple. Okay, as if that pump and the other walls are not needed. So in comparison to your hydrostatic bearing, we can say that the design of your hydrodynamic bearing is much simpler. Okay, now since here the pressure generated, that depends on pressure generated in your hydrodynamic bearing, that is a function of your speed and some other parameters also. But in this particular case, it is solely the required pressure in proportion to the load coming on your shaft, that can be easily controlled by the external means, and therefore the load carrying capacity of your hydrostatic bearing is much higher in comparison to your uh, hydrodynamic bearing. Okay, that is the main advantage of your hydrostatic bearing. Then apart from that, if you remember, yesterday I told you that in case of your this thing hydrodynamic bearing, now at the beginning your shaft is stationary, and when this shaft will start rotating, so that time there will be a friction there will be a friction over the inner surface of your bush and the external surface of your this thing shaft. So due to that, there will be a lot of wastage of the energy. But this particular problem will not come in case of your hydrostatic bearing. So in case of your hydrostatic bearing, there is no initial or the starting friction. That is what you can say. And the contact surface, no contact between that of the sliding surfaces at any, I mean, irrespective of any speed, irrespective of the any load. In case of your hydrostatic bearing, there will not be any direct metal to metal contact between the surface of the shaft and the surface of your bush. I hope I am clear. And as I told you, I think yesterday also we talked about that. As far as the hydrodynamic bearing, yeah, hydrostatic bearing is concerned, so especially the hydrodynamic bearing, so that you are going to classify into two types of bearing. One is the thick film type of lubrication, and the thin film type of lubricated bearing, journal bearing. So in case of your thin film type of bearing, usually what happens, that there is a tendency that the film uh, may collapse under the external load, and hence we call it as a thin film type of lubrication. So when that film is going to collapse under the external loading, so due to that, what is going to happen, the metal to metal contact will happen. That leads to more friction, that leads to the increase in the temperature, and the ultimately the load carrying capacity is going will be affected. So for that reason, that as far as possible, that a thin film lubrication, if that design is perfect, if you are going to control that particular film critically, so in that particular case, that thin film lubrication is okay. But as I said, the chances of that breaking of that particular film are more, and hence that metal to metal, direct metal to metal contact is going to happen. Okay. So for that reason, you will not prefer this particular hydrodynamic, thin film type of lubrication. Now, as I told you yesterday, as far as the functioning of your hydrodynamic bearing, yeah, hydrostatic bearing is concerned. So here you should all of you are aware, whenever we are going to find out the torque transmission capacity of your hydrodynamic bearing. Okay, so in that particular case, uh, you should know that Newton's law of viscosity. I hope all of you are aware of that Newton's law of viscosity. Can any one of you tell me what is the Newton's law of viscosity? Hello, students.
Viscous force is directly proportional to shear in the shear.
Sorry, in the viscous fluid. Yes. What is Newton's law of viscosity? Hello, students. Am I audible? Are you there?
Yes, sir.
Yeah.
Newton says that there is a direct proportional between the shear stress and the viscous force.
See, it said that in case of your a fluid, that shear stress, your shear stress is directly proportional to shear strength. It is proportional to shear strength. Now the question comes, what is meant by your shear strength? So if you remember, just a minute, let me draw one simple figure. See, Yes. So in front of you right now, what I have shown, this is nothing but this is your some fixed surface. This is some fixed boundary, yeah, fixed surface, and over that I have shown, I drawn this three horizontal lines in white color. Okay, over which I have shown three arrows pointing towards the uh, right side. Okay, now basically with the help of this particular figure, what I want to show, these are the different layers in any fluid which are flowing, which are sliding one over the other, one over the other. In case of your solids, in case of your solids, what happens? In case of your solids, we say that shear stress is directly proportional to the this thing. We say that the shear stress is directly proportional to your shear strength. But in case of your fluids, what we say that shear stress shear stress is directly proportional to rate of shear strength, rate of shear strength. I mistakenly written over here at the beginning that this is the shear stress is proportional to your shear strength. So this is valid, this is applicable in case of the solid. But when you are talking about the fluids, so in case of the fluids, we are going to say that as far as that particular shear stress is concerned, so shear stress is directly proportional to your shear strength. So what is the meaning of that? You try to understand that first. Now see here on this particular layer, here some tangential force is acting. So due to this particular tangential force, what is going to happen? The immediate layer, either on the top side or on the bottom side, so that is going to slide with respect to this, but it will slide with some a different velocity. Okay, so if you are going to consider the velocity of this particular layer, okay, so if you consider the layer velocity, say v, and in time, say dt, what is the distance traveled by it? If you have to find out that, so in that particular case, what you are going to do, in amount of time dt, what is the distance traveled by it? So it will be your v dt, barabar, because you say that we say velocity is a rate of change of your displacement. So ds by dt, ds velocity is your ds by dt. So that means that ds is equal to your v times dt. Am I right? So that's the reason here I have written that v times dt. Basically, it is nothing but that is your displacement. That is your displacement. And suppose this is the one point. This is one point which is there on the fixed surface. So this particular point is a stationary, as if at the beginning I clarified that this particular wall is a fixed one, it is a stationary. So that means the velocity of this particular point will become a zero. Velocity of this particular point will become zero. So in the fluid, what we will notice, that as you move away from this particular fixed wall, basically that velocity of your various fluid layers, that is going to vary, that is going to change. Okay, it is going to change. So now let us consider there are two layers, okay, separated by distance, say dy, separated by I mean this is your horizontal x-axis and this is your y-axis. So in that particular case, I will say this is my dy. So if this particular angle, this particular subtended angle is, say suppose at any moment is your phi, so this phi is nothing but that is your shear strength, that is your shear strength. But here what is happening, that angle phi, that is going to change with respect to okay, with respect to time. And that's the reason here what I said, the rate of shear strength. So that means what you mean by the rate of the shear strength? Suppose phi is your shear strength, Phi is your shear strength. So in that particular case, that d phi by dt, that is nothing but that is a rate of shear strength. Am I clear, bacha log?
Yes, sir.
Yes, sir.
And we are saying that tau is directly proportional to your d phi by dt, d phi by dt. Now see here in this particular case, what is happening? What is happening? Further, you can prove that as I have written over here as in my. Achha, I will do one thing. So this is my what? This is your v times dt, v times dt, and this angle is your phi. This angle is your phi. Let us consider this distance is your what? This distance is, say, suppose your dy. This distance is your dy. So in that particular case, that your tan of your phi is equal to what? Tan of phi is equal to your v times dt, v times dt upon your dy, isn't it? Now when this particular phi is very small, so instead of phi, let me write it as d phi. Let us write it as a d phi. What I have written earlier, d phi only, na? Yeah. So let me make one small correction over here. Let us denote that this small angle as a d phi, which is your shear strength. Okay. Now from this particular right angle triangle, what you can write, that tan of your d phi is equal to, this opposite side is v times dt, and this vertical distance, let us say it is a dy. Let us consider the two layers are separated by distance dy. So that means tan of d phi is equal to v times dt divided by your dy. Am I right, bacha log?
Yes, sir.
Yes, sir.
Now when your this thing phi d phi is very small, d phi is very small. So in that particular case, that tan of your d phi is equal to d phi only, and that's the reason you will get this particular relation. Now see, if you are going to take, this particular term dt over here, what you will get, that d phi by dt is equal to v by dy. Okay. So that's the reason, here, that d phi by dt, that is nothing but that is your rate of shear strength, rate of shear strength. And on the other side, this particular term which you are getting, that is known as your velocity gradient, okay. Here the velocity is going to change. Right now here I have taken that velocity v. So instead of that, let us say I am taking this layer ka velocity as v, and this layer ka velocity, let's say v plus dv. So in that particular case here, instead of writing v, I will write dv. Okay. So let me clarify that term v by dy, that is nothing but that is called as your velocity gradient. And hence further, what you can say, that tau is at the beginning I said tau is proportional to your d phi by dt. So similarly you can say that tau is proportional to your proportional to that dv by dt or v by dt. So which is nothing but this is your velocity gradient. Okay. And hence that tau is equal to some constant of proportionality, into your dv by dt. And hence this constant of proportionality is nothing but that is called as your what we call, it is known as the dynamic viscosity, which is the property of that particular fluid. Okay. And which is your dv by dt. Am I right, bachalo? So here,
Sir, it should be
that,
dv by dy, no?
Yes, sir.
yes, I'm very sorry. I'm very sorry. Literally very sorry. Thank you. Here I have written d phi by dt. I'm very sorry. Yeah. So it will be dv by dy. What I have written earlier, Yeah, here I have written V by dy. So dv by dy, and which is your velocity gradient, okay. And here, let me make the correction. Okay, so this particular mu is nothing but that is your dynamic viscosity, which is the property of your fluid. And this particular property of your fluid, that is a function of your temperature. So basically, if you remember, you must be knowing that this viscosity is affected by that of your temperature. Okay, viscosity is affected by that of your temperature. Okay, in case of your liquids, in case of gases, what is the effect of that particular temperature? Can any one of you tell me? Basically, this I didn't talk with you regarding the other properties. That is, there are two important terms which are called as a cohesive force and that of your adhesive force. So basically, it is a cohesion which is responsible for this particular frictional resistance in the fluid. Okay, in the adjacent layers, whatever the resistance that you are getting, that you are experiencing, so that is due to that of your cohesive force, that is due to that of the cohesive force. Okay, so in this particular case, in case of your liquids with a rise of temperature, with increase of temperature, that cohesive force will go on reducing, and hence your resistance also decreases. I mean key that viscosity reduces. Okay, but in case of your this thing, in case of your gases, in case of your gases, um, uh, there will be one more term which we call as angular sorry uh, exchange of the momentum. So that particular thing, that is in case of your gases, that your momentum exchange, so that is going to increase with a rise of temperature, and hence that resistance is going to increase. I mean that viscosity is going to increase. But in case of the liquids, that viscosity reduces with the increase of temperature. So why I'm discussing this particular thing right now over here with you, the reason behind it is that as far as the performance of your hydrodynamic bearing is concerned, so for the performance of your bearing, that mu, yeah, dynamic viscosity, that is a very important property. So viscosity of your lube oil, that is a critical property. So we have to keep in mind with a rise in the temperature, that viscosity in case of your liquid drops, and therefore how much temperature you can allow to increase, what is the maximum temperature that you can permit, yeah, allow to increase, so that you are going to decide based on the allowable, yeah, permissible variation in the value of your viscosity. Okay, am I clear? Hello.
Yes.
So
Yes, sir.
what I was telling you, so from this particular discussion, now it is clear to you that tau is equal to your mu times what, mu times your dv by that of your dy. That is what we said, right? Now uh, uh, so this particular thing, you can also write it. Suppose anyway, in case of in general, what we say, that shear stress is equal to what? That shear force per unit area. Am I right? Shear force per unit area. So as far as that shear force is concerned, suppose I am going to denote that tangential force acting on one particular layer is, suppose, with the notation d phi, and area is, suppose, a, area of layer. I am talking about the area of layer. Okay, I mean I have shown this particular various layers. So I'm talking about this area. I'm talking about this particular area, and I'm talking about this particular df. So this tangential force acting on this particular layer is, say, suppose df, and this particular area is, say, suppose your dA. So in that particular case, that a value of your d phi, df, that will come out that tau times your a, yeah, da, whatever you have to say, isn't it? So since the value of your tau is mu times dv by dy into a, that is the equation that you will get. Am I right? Or if you want to ignore this particular change in the velocity, which is denoted, small change in the velocity, which is denoted here by dv, and the distance between the two adjacent layers, which is denoted here by dy. So if you want to avoid that, you can write it this way: mu times v times area divided by that distance y. Okay, that distance y. Okay, I am talking about the distance along that y axis, which I have shown over here. Okay, let us say this particular distance between the two adjacent layer is y, and this velocity is your v. Okay, so in that particular case, that force, small force df, yeah, instead of saying that small force, let us say f is equal to your mu times your v times a divided by your y. That is what we can write. Am I clear? Acha, one more thing that I forgot. Can any one of you tell me what is the unit of this particular dynamic viscosity? Yes, bacha log. What is the unit of dynamic viscosity? Why you are taking so much time?
Newton per second.
Sorry? Is it Pascal second or Newton per second? Which unit you are telling me? I am talking about
Pascal
the unit
second.
of this. So the unit, as far as the unit of your dynamic viscosity is concerned, it is a Pascal second, or you can say Newton second per meter square. That Newton per meter square, that is your Pascal, and hence you can say Pascal second. So as far as the unit of your viscosity is concerned in SI system, it is a Pascal second. Am I clear?
Yes,
Bacha
sir.
log, yeah. So now let me tell you something. See. So students, see what I tried to show over here. Sorry. Yes. Now see here. This is the your shaft. This one is your shaft. Okay. And this is the difference. Yeah, radial thickness. This is the what you can say. The gap between the radius. This is the difference in the radius of your that of your shaft and that of your the bush. Okay, I mean this particular space that has been filled with your lube oil. So if the diameter of the shaft, if I am going to denote with the notation small capital D, and let us say this particular shaft is rotating with the speed of say capital N. So in that particular case, I will say that this velocity of your this particular surface of the shaft, that will be denoted with the notation pi times capital D into N divided by 60. If this diameter you are taking in meter, then and then only it is possible that I can write this velocity in meters per second. So this is you will get the velocity in meters per second only when this diameter of the shaft is in meters. Am I right? Bachalo. Now here we talked about that velocity gradient, which is your dv by dy, and further we said it is v upon y, and so that v upon y. So if this particular radial clearance you are going to denote with the notation say a capital C, in that particular case, that v by y, in that particular case, that term your v by y, that will become, already here we have written that v is equal to your pi dn upon 60, and as I said this particular y is nothing but that is my radial clearance, and hence in place of this y I'm going to substitute, I'm going to use that clearance C. Okay, यहाँ तक राइट है बच्चा लोग? यहाँ तक समझ में आ रहा है आपको?
Yes, sir.
Now
Yes,
see, yeah. Now see, let us assume that the length of this particular bush, length of this particular your bush is suppose L, suppose L. So in that particular case, what will be the area, or what will be the surface area? Suppose you are going to unwound this particular circumference, so or rather the circumferential area of this particular shaft, that will be your pi d times of L. Do you agree with me? Pi d times of L.
Yes, sir.
So I will say the area of your lube film, or the surface area of your lube film, that is equal to pi into capital D into L, right? So why I am writing this particular thing over here? Because I have written here I have written here the relation for calculating that tangential force, and in the tangential force here that area is involved. So that's the reason which particular area you are going to take. So you are going to consider the area of that lube oil ka surface area of lube oil ka film. Okay, that velocity, how to take it, that I explained. How what is the meaning of mu, that I told you, and what is that y in case of your journal bearing, so that also I discussed with you. So if you are going to write this particular, what we have written, that F is equal to what relation I have shown you just now. F is equal to mu times V times A by Y or C. Okay. So since F is equal to mu times V times A, which is equal to mu into pi dn upon 60. Area, how much it is? It is pi dl upon in place of y, what we decided to write? We decided to write that capital C, right? So that means as far as that tangential force is concerned, what is the intensity of tangential force that I will get? That pi, it will become pi square, right? this mu will remain as it is, and this d, it will give me that d square, then that n into L whole thing upon that 60 C. Am I clear? Are you understanding this?
Yes, sir.
Yes, sir.
Now, yeah. Now, our interest is why we have to do all those things, why we are doing this particular exercise, because here we are going to find out what is the tangential force which is coming on this particular the surface of your shaft. So this intensity of this tangential force coming on the surface of this particular shaft, that we have derived. Now, as already we have said that this diameter of the shaft is capital D. So in that particular case, what will be the torque transmission capacity? The torque will come out that F times capital D by 2. Barabar? Yes or no? Torque transmitted by that of your shaft, that is equal
Yes.
to your F into D by 2. Am I right? And already I have written here that that F is equal to mu into pi square D square N into L by 60 C. So here it is a pi square into mu pi square D square NL, mu pi square D square NL upon 60 into C into you are saying D by 2, right? So that means that torque is equal to again you have one more this thing. So it will come out mu into pi square into D cube into N into L whole thing upon that 60 C, right? Acha, one thing I forgot. Just a minute. Here it will not be a 60 C. It will come out 120 C. Yes, someone was saying something. Yeah. Hello.
So
Bacha
that
log.
was the same thing.
Okay. Okay. So it comes out mu into pi square D cube into NL upon what your 120 C. Now see, if you have this is your a torque, okay, so can I say that this is the torque which is required to overcome the friction between the fluid, okay? Can we say that this is the amount of torque which is needed to overcome the friction between the fluid which is there in the which is there in between the shaft and that of your bush? So if that torque is given by this thing, and already I said that the speed of the shaft is your n. So that means its angular speed is equal to your this thing omega is equal to 2 pi n upon 60. Am I right? So that means this power is equal to power lost due to that of your friction, if I have to calculate. So that power I can calculate by taking a product of that torque and the angular velocity. So again, if you are going to multiply this particular equation by 2 pi n, what I will get? Let me write one thing. Let me write this omega is equal to your 2 pi n by 60 over here. Therefore, that power is equal to if you are going to multiply this torque by omega, what you will get, that mu will remain as it is. That this pi, it will come out pi cube. D cube will remain as it is. This n, it will become n square into L. Okay. Okay. Then here already you have uh, 120, and here you have 2, or I will take it as a pi n by this is pi n upon your 30. So already we have mu pi cube into d cube into n square into your L whole thing upon that 120. 12 threes are how much it is? 12 threes are 36, and this 0 0, so 3600 C. So that will be the amount of power, yeah, amount of power required, yeah, power loss to overcome that fluid friction. That is what you can see. Am I right? Chalo.
Yes, sir.
Yes, sir.
Now, why this particular exercise we are doing? At the end, what is going to happen? Now, right now, I have just explained you ki what is the so right now what I have shown you, I talked about this particular what tangential force. Okay. Now at the same time, I am saying that ki this particular bearing, this one, you are using for supporting what you are using. We are using it for supporting this radial load. Okay, so this is, let's say, my radial load which is coming on the shaft. So if I draw this particular two-dimensional figure, you will understand it. Suppose this is your shaft, so this load is your radial load. This load is your radial load. Am I right, बच्चा लोग? ये समझ में आ रहा है क्या?
Yes, sir.
Now, if this is your radial load, and this radial load has to be supported by the fluid pressure in the, this is the, this in this region, what you have that fluid, and here this particular fluid that will be under the pressure. Let's say that pressure inside this particular fluid is, say, suppose what, P. Let us say this pressure is your P. So we know that pressure is always equal to your force normal force per unit area, isn't it? Normal force per unit area. What do you say, bachcha log?
Yes, sir.
So if that is the case, so in that particular case, that normal force, now in this particular case, which is my normal force? This normal force is nothing but that is your Fr, right? That is your Fr in this particular case. So Fr is equal to your pressure times what, area. Pressure times area. So in just a minute. So your this radial component Fr is nothing but, students, are you there? Am I audible?
Yes, sir.
Yes,
So
sir.
this Fr is equal to your pressure times area. What you say? Now here, as far as that area is concerned, so again, which particular area I supposed to take? I supposed to take that surface area of your bushing, yeah, of your bearing, which we have seen that key, which is your pi d times L. So this Fr ka value will come out pressure times pi into d into L, right? Now With this value of FR, yes, what you are saying?
sir, this D is for pushing, so that will be another notation because small.
Sorry,
They have
sorry,
used
sorry,
for sharp.
sorry.
हमने पहले ही कैपिटल डी यूज कर लिया ना शार्प के लिए तो पुशिंग के लिए कुछ और नोटेशन
No, 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 no. But at the yes, what you are saying, I forgot to tell you one thing. Here, though we are saying that here we have the clearance, but let me tell you one thing. This particular clearance always it is in microns. I mean, though just to make you understand here in all these figures, here you will find that there is a huge clearance, but always in real life situation that particular clearance is in the microns. I mean a diameter of your shaft and the nominal size. I hope suppose if I write that 25 plus minus say 0.5 millimeter. So in this particular case that 25 is my basic size and 25.5 and 24.5. These are your upper limit and lower limit. Are you understanding? So similarly, as far as the this is the how we specify the tolerance in general. Okay, so for your shaft and that of your bush, for your shaft and that of your bush, that inside diameter or the basic size of the shaft and that of your bush are same only, and this particular clearance that is always taken in the microns, and for that reason here I use the same notation. Do you understand why I have used the same? Now I hope I'm clear. I forgot to explain tell you that just to make you understand how this is happening here. For that reason we are showing here the enough clearance, but in real life situation that clearance is always in the microns. Okay, am I clear? Can I go
yes
ahead?
sir.
So now see here, now we calculated the value of FR. We calculated the value of FR. Okay, and we have calculated the value of MT also. I mean, sorry, we calculated the value of that twisting moment also. T torque based on the value of that this thing. What? Based on the value of your what you can say. Based on the value of that tangential force which is coming over here. Where is that? So this is your F ka value. This is your F ka value. Okay. So and I think here we have calculated that term. Yes. So mu into that pi square d cube into L into N. Whole thing divided by that 120. Now just now what I did, I calculated the value of your radial force. I calculated the value of that radial force. Now can I use that particular radial force also for I mean can we calculate the value of that torque by using this radial force, by using this radial force? I mean see here what I mean by that. Let me clarify. So in this particular this is your right. So in that to say your torque is equal to again Fr times your capital D by 2. Am I right? So yes or no? And in that particular case again I have to calculate that a frictional torque. So if I have to calculate that frictional torque, so that value will come out how much? That particular torque value will come out by taking this value of your Fr as mu times P times pi times d square into L whole thing upon your 2, whole thing upon your 2, and this value we are going to equate with that of your pi square d cube into n into L into here it is mu into pi square d cube into n L whole thing upon that 120 c. Okay, so why we are doing this particular exercise? Just to find out the value of that mu, and that mu ka value comes out pi.
Sir,
Yes.
sir, in the left hand equation, mu will not be there.
Sorry, no. You didn't understand why I have taken that particular thing. Here, what I'm saying, I let me clarify why I have taken this particular this mu. I'm talking about the this thing. I'm considering here the torque required to overcome the fluid friction. So when I'm going to consider the torque required to overcome the fluid friction, so that time I need to take into consideration that of the viscosity of your fluid. Do you understand why I have taken? I am considering here which particular torque required to overcome that of your fluid friction. So if I am going to consider that of your torque required to overcome the fluid friction, so in that particular case, that mu term will appear over there. Am I clear? I'm
Sir,
very
we are
sorry. I'm very sorry. Yeah. What you said is right. Yeah. Yeah. So here at the end, what I will get, what I will get here, I will get that mu is equal to after cancelling those particular terms, you will get that pi by 60 into that of your capital D by C into that n into mu uh, here just a minute, that n by that of your pressure. So this is this type of equation you will get. Just a minute, let me show you the same equation that we from PhD which we are using. Just a minute. Yeah. See, just now I tried to derive this particular equation, and this particular your equation that we are that is nothing but that is the equation that is given by your Petrov, and for that reason I used it in some other form. This equation is the same equation I tried to derive just now. And further from that equation only, from this equation only, here if you see this particular graph very carefully, in this particular graph further what they have done, they have taken here on along that x-axis that L by D term. L by D is nothing but that is the ratio of what? Ratio of the length of your bush to the diameter of your shaft, and here along that of your y-axis, here we are taking the viscosity of your lube oil. So as far as this particular graph is concerned, this particular graph is divided in two parts. The graph which is there on the left side, this particular region here, from you can see that the lowermost point in this particular graph, and this particular region, this is called as your boundary region. This is called as your boundary region, and um, and you as far as that hydrodynamic bearing is concerned, so this is the safe zone. This is the safe zone. So this particular region, I mean this part of your graph that is needed for your hydrodynamic bearing, and hence this particular region we call it as a hydrodynamic region. We call it as a hydrodynamic region. So today my intention to derive all those things was to make you understand this a Petrov equation, which is the main equation as far as the design of your hydrodynamic bearing is concerned. Okay. Anyone is having any doubt? Whatever I discussed with you just now, from your exam point of view or from your oral point of view, this equation is very important. Okay. Further, from this particular equation, only one more important term that we are going to discuss, define, that is called as the Sommerfeld number. In the next class, I will talk about that. Right now, let me stop here. Anyone is having any doubt, by the way? Whatever we talked, whatever we discussed till now. If not, then we'll stop. Okay.